In this video, we're going to be discussing moments, centers of mass, and centers of gravity. Sometimes they're the same thing, and sometimes they're not. So first we need to figure out when they're the same and when they're not the same. Let's talk about center of mass first. Center of mass can be thought of as the average location of the mass distribution of the object, or the average location of all the atoms in the object. In other words, this is the point where the number of atoms surrounding that particular point is the same in all directions. Or to put it another way, it's the point where all the particles of the object seem to be concentrated, kind of like they're all piled up on top of that one location. In physics, this is often called the single point mass. If we take an object and we attach it at the center of mass to some kind of board and we give it a push about this point, the object will spin freely while attached at its center of mass without any kind of wobble whatsoever in the rotation. If you build a machine and you've got revolving parts in it or spinning parts, then they'd better be attached at the center of mass or the machine will literally rip itself to pieces. This is what your washing machine is doing when it starts banging around because the load has become unbalanced. It's shaking because the center of mass is no longer where it's rotating. Strangely enough, the center of mass does not actually have to be on the object. Let's take a look at a horseshoe and a donut. The center of mass for a horseshoe is here. Notice that it is slightly lower than the center because there are atoms and molecules here in the bottom, but there are no atoms or molecules here in the opening at the top. That shifts the center of mass down slightly. It is, however, on the line of symmetry between this half and that half. For a donut, assuming it's uniformly dense, we have a center of mass right here in the center of the hole. The hole's not actually on the donut, but that's where the center of the average location of all the atoms and molecules is. So we can think about the center of mass as the weighted average of location with respect to mass, or the number of atoms present. Let's think about if you have an object that's shaped like a flat circular cylinder or some kind of disk, like what we used in the volumes of revolution. Let's suppose one half is composed of lead and the other half is composed of styrofoam. Well, then the center of mass will not be located at the center of the circular part. Instead, it will shift to the side composed of lead. That's because lead is much denser than styrofoam. Generally speaking, density affects the center of mass by shifting it towards the side that is denser, the side that has more atoms and molecules. Now let's talk about the center of gravity. The center of gravity, or COG, is based on weight. Weight is a measure of force. Basically, it's a measure of the gravitational force on an object. That is the effect of gravity on all those individual atoms that are in the mass. That is, it's the point where the pull due to gravity is the same in all directions. If the gravitational field is uniform, meaning it's the same everywhere across the object, then the center of gravity and the center of mass are in the same spot. If, however, the gravitational field changes, is different depending on location of the object, then the center of gravity moves closer to whatever object is producing that gravitational field. The center of mass, on the other hand, stays put. It's the average location of all the atoms and molecules. The center of gravity shifts towards whatever is producing that gravitational field. So in a non-uniform gravitational field, the center of gravity moves towards the object exerting the gravity, whereas the center of mass stays put. If it's a uniform gravitational field from one side of the object to the other, from top to bottom, then the center of mass and center of gravity are the same. The center of gravity is the point where you could balance the object on the tip of a straight pin, and no matter how odd the shape of the object is, it will not rotate and it will not fall off the pin. On Earth, even on Mount Everest, we can usually assume that center of mass and center of gravity are equal if the object is sufficiently small in mass compared to the mass of the Earth and sufficiently small as far as size compared to the radius of the Earth. The ratio of our mass as humans to the Earth's mass is so different that the center of mass and center of gravity are practically the same. They're not exactly the same, but the difference is so minuscule you can't really measure it. This is not true for the Burj Khalifa in Dubai. This is the tallest building in the world since 2010 at just over 2,700 feet. The radius of the Earth is 3,959 miles, or 20.9 million feet. Now you may think, yeah, okay, 2,700 feet is not much compared to 20.9 million. No, it's not, but it's still a significant proportion, and because of that, the gravitational effect at the bottom of this tall building is stronger than the gravitational field at the top. It's not even true for the Empire State Building in New York, which is only 1,250 feet tall. It's still very tall and very dense, made up of a lot of atoms. The center of gravity on the Empire State Building is actually 1 meter below the center of mass. In other words, it's off by 3 feet. That's quite a bit for something that's only 1,250 feet tall, compared to the building in Dubai, which is more than double that. The center of gravity has moved closer to the center of the Earth, which is what is exerting the gravitational field. When we think about the center of mass and the center of gravity, and they're the same, an experimental method for locating the center of mass or center of gravity is to suspend the object from 2 locations and to drop a plumb line from the suspension points. Let's talk about what a plumb line is. A plumb line is basically when you have some kind of weight attached to a string. Since it's weighted, the string will go straight down, pointing towards the center of the Earth due to gravity. When you do this twice, the intersection of the 2 lines is the center of mass, and this may or may not be on the object. If you have a crescent-shaped moon, the center of mass is not on the object, so it'll be impossible to draw the straight line all the way across the object, since part of the line is going to go off the object. There's a YouTube video by David Taylor that does a great job of demonstrating the center of mass when it's equal to the center of gravity. Both of these are links which will take you to that YouTube video. Click on the link and watch the first 7 minutes of the 9-minute YouTube video. In general, think of center of gravity as the weighted average of location with respect to weight, where the weight is the force represented by mass times the local gravitational field G. If G isn't constant over the entire object, then the center of mass and center of gravity will not be in the same place. Skyscrapers are tall enough that the effect of gravity changes over their height. Density will also affect the center of gravity, since the more atoms there are, the greater the gravitational force acting on them. The center of gravity will shift towards the denser side that has more atoms. More atoms, more gravitational force. If the gravitational field is uniform, then remember the center of mass and center of gravity are the same place. Let's now talk about what a centroid is. The centroid, as it sounds, is the center, as in the geometrical center of the object. It is not affected by gravity, and it is not affected by density, as the center of gravity and center of mass are. It's just the average location of all the dots in the object. If the density of the object is uniform, as it would be if it were made of all the same material, all styrofoam, then the center of mass and the centroid would be the same location. If the gravitational field is uniform, meaning from one side to the other of the object, the gravity is the same, and the density is uniform, then all 3 are the same location: center of mass, center of gravity, and the centroid. Here are some pictures of centroids of variously shaped objects. This here is a triangle, and you can see that the centroid is located in the center of the triangle. This is an oddly shaped object with straight, flat sides. The centroid, which is the average location of all the dots that make up the yellow area, is right here. And yes, this is the state of Texas, and the centroid of it has been computed to be right there. That's the geometric center of the state. Notice here that we have 3 purple dots. These 3 dots right here have a geometric center given by the red dot here. This zigzag line segment here has a center as well, which is at the red dot, which is, of course, not on the zigzag shape at all. You'll notice that in this region here with the light blue color, it's also true that the centroid, the average location of all the little blue dots, is here, which is not on the shape at all. But on this particular one, which is a rhombus, it is on the shape. Think of the centroid as the average location of all the points that make up the object. Remember, it does not have to be on the object. Let's summarize what we've learned about the center of mass, the center of gravity, and the centroid. When the gravitational field is constant, center of mass and center of gravity are the same. That won't be true for something that's super tall on Earth, like one of those skyscrapers. When the object is uniformly dense, as it would be if it were made up of entirely the same material, then the center of mass is equal to the geometric center, or the centroid. When the gravitational field is constant and the object is uniformly dense, then all 3 are equal to each other. Now we want to talk about what a moment is. There are different types of moment in physics. What we're talking about is a tendency to rotate. We frequently split this moment into horizontal and vertical components, giving m sub x and m sub y, the moment in the x and the moment in the y. The moment in the x is the tendency to rotate off the x-axis, which, strangely enough, affects the y value. And the second is the tendency to rotate off the y-axis, or a vertical axis, which affects the x value. Let's take a look at a picture to see why this is so. When you have a seesaw and it's balanced perfectly, which this one's not quite perfect, is it? It makes a lovely horizontal x-axis. When it moves, though, it does affect the moment in the x direction. When it shifts off of horizontal, notice that what's changing is the height of the children on the seesaw. The height is the y value. Let's think about the discrete multiple objects case. The moment about an axis is the tendency to rotate off the axis based on the object's weight and the location of the balance point. Typically, we're thinking about rotating off of a vertical or horizontal axis. We compute the moment of a single object, that is, its tendency to rotate, by multiplying its mass by its distance from the point where it would balance. If we have multiple such objects, we can get the total moment of the system to rotate off the x or the y axis by adding each individual moment together. The moment about the x-axis, then, is the sum of all the moments about the x-axis, and the moment about the y-axis is the sum of all the moments about the y-axis. Remember that when you're tending to rotate across this vertical thing right here, what you're adding up is the mass and its distance from that particular axis. So mass 1, which is out here at distance x1, gets added to mass 2 at distance x2, added to mass 3 at distance x3, and mass 4 at distance x4. That will be the tendency for it to rotate off of this vertical axis here. Now, when we're thinking about the moment in the x direction, that's the tendency to rotate off the horizontal line, and that would be the reverse. The center of mass, then, has location given by what we call x bar and y bar. We put the bar over it to represent the average location. X bar is the moment in the y direction, which affects the x coordinate, divided by the total mass. The average location of the y values is given by the moment in the x direction, which changes the y value, divided by the total mass. Let's try to balance some kids on a seesaw. We're going to suppose at first that the fulcrum is located at the origin, 0 on our number line, which is the seesaw. We have kid 1 with mass 1 located a distance of d1 from the fulcrum. He's sitting here on the left side. Kid 2 with mass 2 and a distance of d2 from the fulcrum, where the seesaw balances, is here on the right side. The symbol we use for the location of a fulcrum when we only have one axis is x bar. Where is x bar? To find it, consider that since it's balanced, the total moment about the origin must be 0, since the location of x bar is the moment divided by the total mass. That means that the mass of kid 1 multiplied by his distance from the fulcrum must be equal to the mass of kid 2 multiplied by his distance from the fulcrum. Since the origin is at the fulcrum, and the fulcrum is the place here where it's balancing, and d2 is positive, and d1 is negative. To fix this, we're going to move the origin to the far left side of the seesaw so that all of our values will be positive. When we put the origin here, that changes this distance to x1, and this distance from kid 2 to the origin as x2. Then the fulcrum here will be located at x bar from the origin, which is at the far left end of the seesaw. Now all distances should be positive. We'll rewrite d1 then, the distance from kid 1 to the balance point, the fulcrum, as this value here, x bar minus x1. That's this distance minus this distance, which gives us this distance. Then we'll represent distance 2 from kid 2 to the fulcrum as x2 minus x bar. Now we can express them in terms of where the fulcrum is as m1 d1 equal to m2 d2, as m1 times x bar minus x1 equal to m2 x2 minus x bar, where x1 and x2 are the x coordinates of those locations on the number line. Now we solve for x. Once we have this equation, we can perform a lot of algebraic steps to come up with the value for x bar as m2 times x2 plus m1 times x1 divided by m1 plus m2. That is, the location of the fulcrum, the balancing point, is the total moment, mass times distance, plus mass times distance, divided by total mass, mass 1 plus mass 2. For a total of n objects in the discrete case, we can write this using sigma notation, as x bar is the sum from k equal 1 to n of m sub k x sub k, the total moment in the numerator, divided by the total mass, the sum from k equal 1 to n of m sub k in the denominator. We call the numerator the total moment about the origin, or the first moment about the origin. We call the denominator the total mass. Since these are discrete objects, we can also call these point masses. Let's look now at example 1. Suppose 4 point masses, 4 discrete objects, are placed on a number line as follows. Mass 1 has 12 kilograms of mass, and it's placed at a distance x1, negative 4 meters from the fulcrum. Negative 4 meters means on the left of the fulcrum. Mass 2 of 12 kilograms is placed at x2, which equals 4 meters. Since it's positive, it's on the right. Mass 3, 30 kilograms, is placed at x3, which equals to 2 meters. That would be to the right. Mass 4, 6 kilograms, is placed at x4 of negative 6 meters, which would be to the left. This time, we left the origin in the center, and we're using negative distances instead. Use what you've learned to find the moment of the system with respect to the origin and find the center of mass of the system. Remember that the formula is the total moment of the system divided by the total mass of the system. Let's take a look. Pause the video here, work out the algebra if you can, then turn the video back on to compare your answer to mine. Since it balances, we must have 6 kilograms times negative 6 meters, that's this one on the left, plus 12 kilograms times negative 4 meters, that's this one on the left, plus 30 kilograms times 2 meters, this on the right, plus 12 kilograms times 4 meters, this one on the right. When we add it all together, we get 24 kilogram meters. That's the total moment. Now find the total mass by adding the masses together to get 60 kilograms. The center of mass will be located at 24 kilogram meters divided by 60 kilograms, or at 0.4 meters. We can also apply this same technique to multiple discrete objects in the plane of R2, or in 3 dimensions, R3. Here are the formulas for 2 dimensions. The center of mass is given by the moment in the y direction divided by total mass, moment in the x direction divided by total mass, where the moment in the y direction is given here, and the moment in the x direction is given here. What if, instead of having multiple objects, we instead have just one long, extremely thin wire? If it's thin enough, we'll think of it as being roughly one-dimensional. It's really not. All wires are 3-dimensional. But if it's thin enough, we can think of it as being kind of one-dimensional, where all it has is length and no width and no height. How can we find the point at which that thin wire would balance? And we'll call that point x bar. Remember, if the density of the thin wire is uniform, meaning constant all along the wire, as it would be if the wire were made of one material, then the balance point, the center of mass, will also be the centroid, the geometric center. And that's easy. All you have to do is take the length of the wire and divide by 2. Then the center of mass, which will equal the center of gravity, provided it's not so long as one of the skyscrapers, will be equal to the centroid. And that fulcrum will be the distance from either end of the wire. What, on the other hand, if it's not uniform density? Now we're going to suppose that the density varies along the length of the wire. Maybe it's made of all aluminum at one end, which is about 2.7 grams per cubic centimeter, and all tungsten at the other, which is quite dense at 19.3 grams per cubic centimeter. Tungsten is even denser than lead. And a mixture of the two between. Yes, I know, these are measured in volume, but we're pretending here. So pretend it's so thin, it's practically one-dimensional. We can express the density as rho of x. Remember, this is the Greek letter rho, or r, and put the origin at one end of the wire, usually the left. Now we're going to chop the wire into teeny tiny pieces. Yeah, you know what's coming. So the density, rho of x, is practically constant over that tiny little length. Now pick your favorite location in the kth slice, say x sub k, and compute its moment. The mass is roughly rho times x sub k times delta x. The distance from the center of mass is x sub k minus x bar. Here's what it might look like to chop up a very, very thin wire. Note that we put the origin at the left end of the wire. Now we're going to sum up all the moments on all the little slices of wire. They should equal 0 since they're going to be balanced at wherever x bar is. Taking the limit leads to the following expression. 0 will be equal to the limit as delta x goes to 0, or the number of cuts in the wire goes to infinity, of the density rho at our particular favorite spot in each cut, x sub k, times x sub k minus x bar, that's the distance from the little point to where it balances, times delta x, the width or length of each little cut. When we put this into the definite integral after taking the limit of the Riemann sum, we have rho of x times x minus x bar dx. Now, if we take this formula and we distribute the rho of x, we get x rho of x dx minus the integral of x bar times rho of x dx. But x bar is at a fixed location. It's where this thing balances. It's a constant, and it can be taken out of the integral. That means, since this is equal to 0, that we can move this negative integral to the other side of the equation and get that x bar times the integral of rho of x dx is equal to the integral from a to b of x rho of x dx. And that leads to the formula for the location of x bar, the total moment x rho of x dx integrated from a to b divided by rho of x dx integrated from a to b. Again, the formula is the total moment, which is mass times distance, divided by total mass. Remember that rho of x dx will give us the mass, and then mass times distance gives us total moment. In the denominator, rho of x dx gives us total mass when we integrate from a to b. What if we have a super thin plate called a lamina? A lamina is basically something that is two-dimensional, length and width, but no depth. In other words, it's infinitely flat. It's kind of like a piece of paper if the piece of paper didn't have any, well, thickness to it, which you know it does, because when you pile them together into a ream 500 pages thick, it's about 2.5 inches. It does have thickness. It's just very small. Think about a thin plate with no thickness, and let's find the center of mass, which will be the centroid if it's small enough, by computing x bar y bar equal to the moment in the y direction, or the tendency to rotate off of that y-axis, which changes the x value, and the moment in the x direction, which of course is the tendency to rotate off the x-axis, which changes the y value, divided by total mass. What's the meaning of the picture? Well, these are uniformly dense plates, which are really flat, and they're spinning. They're spinning in the air, and the point where the stick is touching the plate is located at the center of mass, or the centroid. That's why they're spinning freely, without any wobble, and without falling off. The reason they're not falling off is partly due to the force with which it's spinning, but also due to the fact that the center of mass and the centroid and the center of gravity are all located in the same location, right there where the stick touches the plate. Let's talk about the symmetry principle. If a region is symmetric about a line L, then the centroid or geometric center of the region lies on that line. If the shape has uniform density, then both the centroid and the center of mass are the same, so they both have to be on that line. Remember though, if the lamina does not have uniform density, then we have to find the mass by integrating across the region. We're going to look at a couple of different cases. This is constant density, which is case 1. A lamina with line segments for the left side, the right side, and the bottom edges, and rho being a constant over some two-dimensional region R. It's bounded by the function f of x above, the x-axis below, on the left by the vertical line x equal a, and on the right by the vertical line x equal b. It's going to look kind of like this picture that you see here. The vertical line x equal a, the vertical line x equal b, the x-axis y equals 0, and some kind of curve for the top. Our mass is given here by rho times the integral of f of x dx. Notice that rho is a constant, so it comes out of the integral. The moment in the x direction is given by this formula, rho times the integral from a to b of f of x squared divided by 2 dx. The moment in the y direction is given by the definite integral rho, which is a constant here, times the integral from a to b of x times the function dx. What do you notice about all three of these integrals? I hope you've noticed that they all have the differential dx, which is a little surprising for the moment in the y direction, but that's just the way it goes. Or actually, it should be more surprising for the moment in the x direction, since that actually affects the y variable. But again, notice that all of these formulas have been written with respect to x with a differential of dx. Our center of mass will be x bar y bar, which is the moment in the y direction divided by total mass, moment in the x direction divided by total mass. In this case, the density is going to cancel out of the location of the center of mass and, of course, the centroid, since our density is constant, because the density is constant. Rho divided by rho gives you 1, so it cancels out of both, and we end up with this formula here. What if the density is not uniform? Let's look at case 2. The density is not uniform, but we still have a lamina with line segments on the left, the right, and the bottom, and some kind of curved edge for the top. Notice that the change that has occurred inside of our formulas for mass, moment in the x direction, and moment in the y direction is that rho is no longer constant, so it cannot come out of the definite integrals. Rho depends on x, so it has to stay inside the definite integral. In this class, we will only examine density functions that are functions of x and not y. In Calculus 3, you'll take a look at density functions that depend on both x and y, but those require double integrals to compute. Again, the formula for center of mass is x bar y bar, total moment in the y divided by total mass, moment in the x divided by total mass. Notice here that the density does not cancel out because it is not a constant and it depends on x, which is what the integral depends on. Notice that all the formulas again have differential dx and are written in terms of x. The shape is essentially the same, it's just that the density is not constant. Maybe this end is made of styrofoam, the middle is made of aluminum, then it's lead, and then it's tungsten. So it gets progressively thicker as we move across. In other words, there are more and more atoms as we move across the object from left to right. Let's take a look now at example 2. Let R be the region bounded above by the graph of the function f of x equal x squared and below by the x-axis over the interval from 0 to 2. We want to find the centroid of the region. Remember, the centroid will be at the center of mass if the density is uniform, meaning constant. If the density is constant, it cancels out of the formula. Let's take a look now at what we would have. Because we have constant density, it cancels out of our formula, and you notice that it does not appear here. In fact, rho was not given up here at all. That's because to find the centroid, we assume that rho is a constant, so it cancels out. We need to compute these two integrals. The denominator, of course, will be giving us the area. Area times density would give us mass. In this case, because the density cancels out, it just gives us area, which gives us 8/3. Now we need to find the moment in the y direction and the moment in the x direction. For x bar, we need to compute the following. We take the moment in the y direction and we divide it by the area. Well, actually, close to the moment in the y direction. We're missing our rho. When we do this, we'll have x times the function on top, which is x times x squared, which gives us x cubed. The integral is x to the 4th over 4, which gives us a moment, total moment of 4. 4 divided by 8/3 should give us x bar. Now let's look at the moment in the x direction, which of course changes the y value. The formula is 1/2 the function value squared dx. Notice that this gives us x to the fourth, which when integrated gives us x to the fifth over 5. This will result in 16 over 5. Take that value and divide by the area. This gives you 3/2, 6/5. Let's take a look at where that would be on the shape. We found that the center of mass is equal to the centroid because we assumed we had uniform or constant density, and that gave us 3/2, 6/5. That's located here at the black dot within this shape. It's hard to imagine that that really is the centroid, the geometric center, and the center of mass, the average location of all the atoms and molecules that make up this uniformly dense region. But it is. That's where it would rotate and spin freely without any wobble in the rotation. Let's look at case 3. In case 3, we have a lamina again and constant density. But this time, we have curves on both the top and the bottom and straight line segments for the left and right edges. In this case, since we have constant density, rho can be factored out of the definite integrals in all three cases for the two moments and the mass. Our center of mass will be given by x bar, y bar, and since our density is constant, it'll also be the centroid. This time, though, we have a function on top and a function on bottom. How is this going to affect things? Keep in mind that these formulas can also be adjusted to be functions of y as well, where we have a function of y on the right and a function of y on the left. The density will again cancel out because it is a constant. Let's take a look now at example 3. Let R be the region bounded above by the graph of the function 6 minus x squared, a downward opening parabola, and below by the graph of the function g of x equal 3 minus 2x, a negatively sloped line. Find the centroid of the region. We can find the centroid without anything for the density because we'll assume the density is constant and will cancel out. You can see the region here outlined in blue. And notice that these two curves intersect at -1, 5 and 3, -3. Let's now write down our formulas and compute the centroid of the region. Since rho is a constant, it will factor out and cancel. The moment in the y direction is given by rho times x times the difference between f of x and g of x. The rho will cancel out, so we get x times f of x minus g of x for the numerator, and f of x minus g of x for the denominator, since again, for the mass, the rho canceled. Then we take the moment in the x direction, the tendency to rotate off the x-axis, which affects the y value, and that's given by rho times the definite integral of the squares of each of them subtracted. Then, of course, we again divide by the mass, rho times f of x minus g of x, but with the rho's canceled. Now let's take a look to see what we get when we compute these. First, note that f of x minus g of x is the upper function, the downward opening parabola, 6 minus x squared, minus the negatively sloped line, 3 minus 2x. That gives us negative x squared plus 2x plus 3. To compute the area under the curve, we simply take the definite integral from -1 to 3, from where they intersect at -1, 5 to where they intersect at 3, -3. And that gives us 32/3. Then to find x bar, we take the moment in the y direction divided by rho, of course, and divide it by that particular value for the area, 32/3. Remember, the formula is x times f of x minus g of x, which is given here by this trinomial. When we compute that, we end up with x bar being at 1. Now we need to find the y bar by taking the moment in the x direction, that tendency to rotate off the horizontal seesaw, and that is computed by taking rho times the difference of the squares of the functions. Since we're dividing by row, that gives us, if you work out the algebra and the calculus, 832 divided by 30. Then we again divide by 32 thirds, and that gives us 13 fifths. Our center of mass is located at the centroid, the geometric center, since our density is constant, and that's located at the ordered pair 1, 13 fifths, or 1, 2.6. Let's locate where that would be on the region. Here you can see the two curves and the region in green between them, with the center of mass, which is equal to the centroid, marked here in black. We have one case left to consider. This is case 4 with non-uniform density, where the density depends only on x, and we have line segments for the left and right edges, but we have curves for the top and the bottom. Since our density now depends on x, it cannot be factored out of the definite integral, and will have to stay in each of the integrals until after the integration is complete. It cannot cancel out, even though it appears in both the numerator and denominator of the centroids and the center of mass functions. Let's take a look now at what this would look like. The center of mass would again be x bar, y bar, the total moment divided by total mass. If we have a function of x, it will look like this. If we have a function of y, it will look like this, where they're left and right instead of above and below. Let's work example 4. We want to calculate the mass, the moments in the x and the y, and the center of mass for the region between the curves y equal x and y equal x squared, with the density function given by rho of x equal x in the interval from 0 to 1. Of course, we're using the interval from 0 to 1 because that is where the curve y equal x, the line, intersects the parabola y equal to x squared, as you can see in the picture here. First, notice that the formula for the mass is the density rho of x times the difference between the two curves, f of x minus g of x. Let's compute it now. Remember that the density function is given by x, and that is the x that appears here. The x that appears here is the line y equal to x, and the x squared is from the parabola y equal x squared. This gives us density times the difference in the two curves. When you multiply it out and perform the integration, you end up with 1/12. That's the mass for that particular region. Now we need to compute the moment in the x, the tendency to rotate off the horizontal, which will change the y value and will be a part of y bar. This time we have rho of x, which is again x, multiplied by the difference between the squares of the function, all divided by 2. When we compute that, we come up with 1/24. This is the tendency to rotate off of the horizontal like a seesaw does. Let's now look at the moment in the y direction, which is given by x times rho of x times the difference in the two curves. This x is not the density function rho of x, but is an additional x in the formula. That gives us x times x, or x squared, multiplied by the difference in the two curves. When you perform the integration, you should come up with 1/20. In order to find the center of mass, we take the moment in each direction and divide by the total mass. The x bar is given by the moment in the y direction, the tendency to rotate off the vertical, which will affect the x coordinate, and divide it by the total mass, 1/12. This reduces to 12/20, which becomes 3/5. The y bar is given by the moment in the x direction, the tendency to rotate up or down from the horizontal, which affects the y value. That's given by 1 over 24 divided by the total mass, 1 over 12. That becomes 12 over 24, or 1/2. This gives us center of mass located at 3/5, 1/2, which is marked here with the black dot. Notice that this is definitely not the centroid of the shape, and that's because its density depends on x. As x increases, it becomes more dense. Since that's true, we would expect the center of mass to shift to the right towards where the more dense atoms and molecules are, and that is exactly what's happened. This is the end of the video covering center of mass, center of gravity, and the centroid.